All right, good morning, folks.
Good morning.
So I'm going to be passing around my little yellow pad here. You'll see on the first sheet it says Saturday workshop. Second page is Sunday workshop. Third page is Tuesday workshop. I need you to print your name on the one that you're going to come to so I can kind of get an idea of whether I need to really hold three or not. Okay, so I'll pass it around. Put your name on the workshop that you intend to attend. Did everybody get the email and Canvas about what I'm expecting? Okay. So just to kind of clarify just a little bit more there, you're going to come in and you're going to rework your exam. Okay? When you're done with that, I'm going to grade it. I'm going to look at it. But you will get half your missed points for coming to the workshop and working the entire exam, asking questions and working along. Okay? So that's going to be the deal. Everybody clear with that? Okay, so as the sheet is walking around, mark which day you intend to attend the workshop. And the workshops will be up on the 4th floor.
If we end up coming on a different day, is that okay? So,
Yeah, it'll be okay. I'm just trying to get an idea of what to expect, how much room I'm going to.
Or you can write like maybe your name.
right,
And
because I
then
hadn't
maybe your
fully
name.
decided yet.
Yeah.
Okay, you can do that.
That's all.
All right, there was one slide that we didn't get to last meeting, and it was on the oxidation of substituted benzenes. And when you have an alkyl group on an aromatic ring, or a benzene ring, so here we have, what would we name this?
Toluene.
Toluene is the common name, but you could also name it
Methylbenzene.
methylbenzene, right? So if you look at this carbon that is directly attached to the aromatic ring, this carbon is called a benzylic carbon atom. Okay, so any carbon atom directly attached to a benzene ring is called a benzylic carbon atom. And they have special reactivity. Okay, if you take a molecule, okay, an aromatic molecule that has a benzylic carbon, and that benzylic carbon has at least one hydrogen atom attached to it, it can undergo oxidation. So you can oxidize, again, remember, O in bracket means general oxidation. You can oxidize those benzylic carbons to new functional groups. And in this case, you can oxidize it to a carboxylic acid. Okay? So I can take toluene, fingernail polish remover. I can oxidize it to benzoic acid, which is actually the acid that is used to make sodium benzoate, which is used to preserve your food. Yeah, especially if you've ever gotten a package of soy sauce. Read the back of the packet, it'll say contains sodium benzoate. They can make that from crude oil. This is where we get toluene. So you can take toluene, oxidize it to benzoic acid, and you can have a food preservative, or the precursor to a food preservative. Okay? Now on my slide, I am showing the oxidant being potassium permanganate, KMNO4. KMNO4 will do this reaction. Your book talks about the chromium reagents. Okay, so CrO3, H2SO4 will also do this reaction. Okay? You have to have a strong oxidant. But what you need to see here is that it will oxidize any benzylic carbon that has at least one hydrogen. So toluene gives me benzoic acid, but so does isopropyl benzene. That carbon is the benzylic carbon and it has one hydrogen. It will also undergo oxidation to benzoic acid. If you look at diethyl benzene, now should I name that diethyl? I need some more to that name, don't I? How would I name that?
Was it the P?
What's P mean?
There?
Para. Is para,
1,4.
para is 1,4.
Mm-hmm.
Right, so they would be on opposite ends.
That would be O.
Oh, yeah, this is 1,2 diethylbenzene or ortho diethylbenzene. We can react that with a lot of potassium permanganate and in fact get phthalic acid, this 1,2 dicarboxylic acid. Phthalic acid is used to make polymers. Okay, they can make that from diethylbenzene. But notice if I took terbutylbenzene, which is this, notice that benzoic carbon, how many hydrogens does it have?
0.
0. When I subject it to oxidation, no reaction.
In the isopropyl benzene, what happens to the two methyl groups?
They get oxidized to carbon dioxide ultimately. Yeah.
Okay.
Yep. You got to have at least one hydrogen bound to the benzoic carbon for this to happen. Okay?
And it always becomes carboxylic acid.
Yes.
Okay.
Yep. And what we're showing here, that is correct. Okay? It's a complicated free radical mechanism. We haven't even talked about free radicals. I don't care that you know any of that. Okay? You need to know, though, that you can convert a benzoic carbon to a carboxylic acid on aromatic rings pretty easily. Okay? So, somebody's already asked, why am I wearing 2 pairs of glasses? These are safety glasses, so I'm going to put on the safety glasses. And I'm going to put on some gloves. If I can find the, there we go,
The thumb.
the thumb. We're going to do the demonstration, I promised. So, last time we talked about the fact that aromatic rings have something special about them, right? So if I take benzene and I react that with bromine, what do I get?
Nothing. Just
No reaction. Benzene does not undergo addition reactions. Okay? However, if I take something that starts to look like benzene, but not quite, like cyclohexene, and I react that with bromine, what's the product?
The 2 bromines coming out trans.
Yep, that is right. So I add bromine across the carbon-carbon double bond, right?
Yeah.
Now, interestingly enough, I happen to have both of these molecules here with me, or all 3 of these molecules with me, I should say. So here, what do you all think that is?
bromine.
Do you have a question?
Yeah, what did you say the benzene doesn't go through?
It doesn't undergo addition reactions. So that is a solution of bromine. It's really just maybe 1/4 of a milliliter of bromine, and the rest of it is dichloromethane, CH2CO2. And notice the color. How would you describe that color? We get it on the film here, or on the video. All right. How would you describe that color?
Brownish red.
Brownish, orange, red. Yeah, it's kind of the things that we typically see. Okay? Bromine is colored this way because the molecule bromine, the BR-BR, has electrons that sit in one of the molecular orbitals. It absorbs light, and one of those electrons will get promoted to the next highest orbital. And it happens to be able to, the energy needed to do that is in the visible region. So it's absorbing certain light and reflecting the rest. And it's because electrons are moving from one orbital to the next. Okay? It's because an electron is moving from one orbital to the other.
What's happening?
So it absorbs light, and when it absorbs light, that electron gets moved from a lower orbital to a higher energy orbital. So it's absorbing a certain piece of the light wavelength, and it's reflecting the rest of it, and that's why it looks the way that it looks. So since it kind of looks reddish, what color is it absorbing?
The other color outside of red.
The other color except red. Okay, that narrows it down, Jason.
green.
Yeah, more on the bluish side of the spectrum, right? So it's absorbing more in the bluish region and it's reflecting back kind of the reddish region, right? So it kind of does look like blood, doesn't it? Yeah. It wouldn't be a very healthy blood, but it does kind of look like that. All right. Now here, I've got a sample of cyclohexene. Okay? How would you describe that?
Clear.
That's clear, colorless, kind of looks like water, right? And then here, I have our good friend benzene. How would you describe that?
Carcinogenic.
Well, I mean the appearance.
Clear.
Clear, right? So you would say that cyclohexene and benzene kind of look similar, right? You really can't tell one from the other, right? If I did this, you probably wouldn't be able to tell much happened, right? Okay, but we're going to test the hypothesis of whether or not this is true. Right? We hypothesize that bromine will not add to benzene, but that it will add to a regular, just old alkene like cyclohexene. Okay. Now it turns out that when you break the bromine-bromine bond, you get rid of all those orbitals that I was telling you give rise to the color of molecular bromine. So alkyl halides are colorless. Okay, so what should happen if we add bromine then to benzene? What should we observe?
Still color.
It'll still be colored. It'll look more like a dilute bromine, but it'll be. But what about here?
Colorless.
Kind of should be colorless, right? All right. So let's start off with cyclohexene. Okay. Oops.
Does benzene vaporizes in room temperature?
It does. So you might smell a little bit of odor. Don't worry. I'm going to take a little bit of bromine here. Notice what happens.
It's gone.
It's gone. Still looks colorless, doesn't it? Right? So what's happened?
It reacts to make alkyl halide.
Yeah, we made this, didn't we? Right? Not completely. I still have cyclohexene around. I didn't add
Oh,
enough.
yeah.
But now let's do benzene. And what do we predict?
That the color won't go in?
Okay.
Dilute
It
it.
won't react? These are all alkyl halides, like translucent, like clear.
Mm-hmm.
Oh.
What do you think will happen when I come back tomorrow? Nothing will happen. This will still be colorless. This will still be kind of oranges. That still looks like bromine, doesn't it? Just bromine and benzene now, right? No reaction. So what does that mean for benzene?
That it doesn't react.
Doesn't react.
Doesn't react, right? But what else does it mean?
Very stable.
It's very stable, right? We know that the benzene really isn't 3 double bonds, is it? It's much lower than that. It doesn't do addition chemistry. It doesn't want to react. And it turns out that benzene is not the only aromatic compound, and you all are alive today because of aromatic compounds, okay? Your DNA contains bases, right? You've probably learned about the DNA bases, right? They are aromatic systems. They are stable. That's why we can go and find a decomposed whatever from 1 million years ago, and we can extract DNA from it still today, because it's an aromatic system that doesn't like to react very well. Okay? Yes, it will degrade over long, long periods of time, but you can still, to this day, you can go dig somebody up, right? You can test their DNA even hundreds of years after they have passed on. And so it has to do with the fact that they have aromatic rings in those DNA bases. Okay? So that was the demonstration that I wanted to show. So I'm glad I was able to get you to see that. And so today we're going to try to do our best to get through the rest of Chapter 9, that's right. We do have a quiz today, that is right. Chapter 8. So last time we learned that there are 4 things that are required for aromatic systems. What are they?
Cyclic.
Cyclic. The molecule must be cyclic. Meaning, right, that I start at one point and I go all the way around without ever lifting my pencil or pen, and I get to the starting point, right? That would be a cyclic molecule. Okay, so that's rule number 1. Rule number 2, it has to be planar. Right? It has to be flat on the plane of a surface, right? So I showed you that. Obviously, cyclohexane is not planar. It's like a chair, okay? But we're not there yet, right? So this would not be aromatic. Even though it's cyclic, it's not planar. Can't be, right? Rule number 3, has to be conjugated. Meaning what?
Alternating double bond.
Okay, so you have to have alternating double single bonds all the way within the ring of the system, right? Benzene has that. Okay? So it's cyclic, it's planar, it's conjugated. Conjugation means that each one of these carbon atoms has a p orbital on it. Okay? And rule number 4. Huckel's rule, which is
4n plus 2
4n plus 2 equals what?
integer.
No, n equals an integer, but what is 4n plus 2 equals to? I heard it. Pi electrons. Pi electrons, right? So how many pi electrons does benzene have? We've got 6. Is equal to 2 plus 4 times n. So 4n equal 4, n equal 1. That satisfies Huckel's rule. We're good. No problem. Right? No problem whatsoever. Does that make sense? Each and every one of these rules must be satisfied for a system to be aromatic. You can't go, well, it satisfies 3 of 4, so it's 3/4 aromatic. That's not the way this works. You have to have a smiley face on each and every one of these, all the way down. Okay? It's got to be satisfied. Okay? You will have to identify aromatic systems on the next exam. I'll draw things like the annulines or whatever. I'll tell you, you assume that they're all planar. Which of the following are aromatic? Okay? Know all 4 of these rules. Now, we just learned that aromatic systems are very stable. They don't like to undergo addition reactions. I take a peek in here. Still colored. No addition has occurred. Cyclohexene, still colorless, right? Addition reactions occurred very, very quickly. Okay? But that doesn't mean that aromatic rings don't undergo chemistry. They do what's called electrophilic aromatic substitution, or as we organic chemists like to call it, EAS. Electrophilic aromatic substitution. What do those 3 words mean to you? Let's start with the first one, electrophilic.
Like electrons.
Like electrons. Okay, what does? The benzene ring?
No.
No. It will react with some type of electrophile. right? Benzene likes to react with electrophiles. Aromatic, meaning that we're dealing with an aromatic system, like benzene. And substitution, what does substitution mean?
Means you substitute one thing for another.
Okay, and what might that other thing be here? What are we substituting? Okay, we're going to put the electrophile on the benzene ring and substitute what for it? We're going to remove the hydrogen. Right, so we're going to do a hydrogen electrophile swap. Okay, so if you think about, and I'm just drawing in one hydrogen, of course there are 6 of them. E plus is the generic term for electrophile. This is the kind of chemistry that benzene likes to do. And so today we're going to talk about that. We're going to talk about different types of electrophilic aromatic substitution, and you'll see why this is so important at the end of the day. Okay?
Is the electrophile always positive or?
Not necessarily always formally positive, but they behave like they're positive. They want electrons. Okay? Things that want electrons are electrophiles. And so I just gave you that general reaction, right? Benzene ring plus an electrophile reacts to give an electrophile substituted benzene ring, and we're replacing that hydrogen with the electrophile. We know just from the demonstration we just did that addition reactions are not favored in aromatic systems. The reason is, if you look at it, we know that the starting benzene ring is aromatic. Is the product aromatic?
No,
Why is it not aromatic? It's cyclic,
not completely conjugated.
not completely conjugated,
Not satisfy Huckel's rule.
doesn't satisfy Huckel's rule, and it's not planar. It's not planar anymore. You can't tell that from that, but if you built the model, you would see that it would start to pucker. Okay? So the product here is not aromatic. So what does that tell you about the product's energy or stability?
Higher.
It's higher in energy, which means it's less stable. So going from something that's really stable to something that's very unstable, relatively speaking, does that seem like that should happen? No. Okay? So benzene does not like to do addition reactions. However, when we look at substitution, what can we say about the left and the right?
Both are aromatic.
That's right. I look on the left, I go, well, it's cyclic, it's planar, it's completely conjugated, it satisfies Huckel's rule. If I look on the right, I go, well, hey, that's cyclic, it's planar, it's completely conjugated, and it still satisfies Huckel's rule. So it still remains very stable. Okay? So it's all about this aromaticity. And you'll hear organic chemists quite frequently call this kind of thing a driving force. Okay, the driving force for this electrophilic aromatic substitution is the fact that it remains stable. Okay? It remains aromatic and is stable.
So it's because of that product that it undergoes substitution but not addition.
That's right. That is exactly right. Okay? You're going to need to know each and every one of these reactions. Okay? I can add a halogen to an aromatic ring, but it's not addition. It's substituting the chlorine or the hydrogen for chlorine or bromine. This really only works for chlorine and bromine. Okay? Notice what's different there. What's in that equation that is not in my little flask here?
Iron.
Iron. You need a catalyst for this to work. Okay, you've got to generate a Br plus or a Cl plus. Does that seem possible? What's weird about bromine plus and Cl plus?
Doesn't satisfy Octet's rule.
Doesn't satisfy Octet's rule. What else? Where is bromine and chlorine on the periodic table?
7.
They're pretty close to fluorine, right? So they're very electronegative. Would electronegative things want to be positively charged? No. Right? So we got to throw something else in there to do that, and that's iron, either trichloride or tribromide. You can do that reaction. We can actually put a nitro group, NO2, onto a benzene ring. The electrophile is NO2 plus. Okay? You use a mixture of nitric acid and sulfuric acid for this reaction to occur. It's called nitration. Okay? It's one of the common ways to do electrophilic aromatic substitution on an aromatic ring. Very useful reaction. We can place an SO3H group on a benzene ring. Benzene reacts with SO3 in the presence of sulfuric acid. Sulfuric acid for these is a solvent. And you get benzene sulfonic acid. This is a nice acid, very strong acid. This is how you make detergents, for example. Detergents are quite frequently made with sulfonic acids. Okay? So this is a very useful reaction. All three of these reactions that I've just talked about, notice that the carbon electrophile bond is between carbon and a heteroatom, right? So chlorine's not carbon, nitrogen's not carbon, sulfur's not carbon. But we can also make carbon-carbon bonds by these reactions called Friedel-Crafts reactions. Friedel-Crafts, two individuals that developed these reactions. And what you'll notice, which is very, very important here, is we're making a carbon-carbon bond. Where R is some alkyl group, we're making a carbon-carbon bond. Believe it or not, the toughest thing in all of organic chemistry is how to make carbon-carbon bonds. There's only a handful of ways to do it. The Friedel-Crafts reaction is one of them. Okay? But it has to be with an aromatic ring.
It has to be alpha chloride.
It can be bromide
Okay.
as well, but typically we do the chlorides. They're cheaper. Notice what the electrophile is. What is that? If I say R+, what would that be?
Carbocation.
It's a carbocation. So carbocations will react with aromatic rings to make carbon-carbon bonds. Wait a second, if we're dealing with carbocations, what do I need to pay attention to?
Rearrangement.
Rearrangements. What do we remember about rearrangements?
They want to be on a degree 3.
That's right. So we want to have a more stable carbocation, right? So if you generate a carbocation, what's the rule I told you? You stop and think about whether or not it can rearrange to a more stable carbocation. That will happen in the Friedel-Crafts alkylation reaction.
Just for clarification's sake, for the Friedel-Crafts calculations, the R's are just like placeholders, right?
Yeah, it's just a generic carbon alkyl group. Okay? There is also the Friedel-Crafts acylation reaction, which uses what's called an acid chloride. We'll talk about that a little bit in a moment, but it's got a carbonyl group. Notice what it makes. It makes a carbon-carbon bond, but to a C double bond O. So you can take benzene and make it into some type of ketone. Okay? These, the electrophile does not rearrange. And we'll learn why that is in just a moment. Okay? It doesn't make a typical carbocation. We'll learn a little bit about that as well.
So the carbocation doesn't arrange?
It does not in the Friedel-Crafts acylation. And the reason is because it's really not a carbocation. I'll show you why here in a little bit. Okay?
So it doesn't react with carbocations because they're so unstable, so it doesn't even matter how stable.
That's right. Well, close. What is a carbocation? It's a positively charged carbon. What does it want? It wants electrons. Where are there electrons? The benzene ring has pi electrons. You're going to get a reaction happening. Okay? And it can happen because the product ends up being stable as well. Okay? Does it matter how you generate the carbocation? No. You could generate carbocations from alcohols, and they'll add to benzene. You can generate carbocations by the Friedel-Crafts alkylation, they'll add to benzene. Any carbocation will technically add to an aromatic system and do electrophilic aromatic substitution. So you need to know these 5 reactions. If I want to make a, let's say, bromobenzene from benzene, what am I going to use?
Iron.
I'm going to use iron tribromide and
The bromine.
Br2. Yep, I can do that.
And
If-
it has to be BR2, not just BR.
Has to be Br2. You can't just buy Br. Right? That's okay. If I want to make nitrobenzene, I want to make a carbon-nitrogen bond to the aromatic ring. I'm going to use a mixture of nitric acid and sulfuric acid. If I want to make a sulfonic acid, I'm going to use SO3 and H2SO4. If I want to make a carbon-carbon bond, I'm going to use the Friedel-Crafts alkylation reaction. And if I want to make a ketone, I'm going to use the Friedel-Crafts acylation. Okay? Any questions about that? We'll get to the details here in just a moment. Let's work our way through the general reaction mechanism of any electrophile. Let's just say we're going to use E+. So I've got benzene. And I've got E+. Can I have just a bottle of E+? What else must I have?
Catalyst.
Okay, not the catalyst. I have to have a counter ion, right?
Uh-huh.
So let's just generically say it's X minus.
Okay.
So I got to have something like that, right?
Is X like a halide?
It could be anything. It could be a halide. We'll see what X minus is as we get out of the general reaction mechanism and we start looking at some of the other stuff. Okay, so the electrophile is positively charged, the counter ion is negatively charged. We throw that into benzene. What do you think the first step is?
The electrophile attaches.
How? How would I draw that? You're right. How do I draw that?
From the double bond of the benzene.
Okay, from the double bond, what do I draw?
And
An arrow.
to the positive.
Okay, very good. So I'm going to draw an arrow from here to here, right? Which means that one of these carbons of the double bond, it doesn't matter which because they're all identical, is going to form a bond to the electrophile, right? All right. So I'm just going to pick on the top one. And we know there's a hydrogen there, and I'm going to draw that in, right? So there's a hydrogen there, so let's draw that in over here too. And now, as Selena said, we've made the bond to the electrophile. And we still have our X minus out here somewhere, right? So this double bond is now made a bond from this carbon to the electrophile. These electrons were what was in that double bond, right? You'll see that? This double bond and this double bond, did anything happen to them? No. So I'm going to draw them in right where they're at. Now wait a second. I have a positive charge, a negative charge, and now I only have a negative charge. Is that right?
No, it has to be a positive.
Where do I put the positive charge?
On the E from the H.
If I put it here, that won't work. Why not?
Okay.
Because I'm giving electrons to a positively charged thing, so it's got to be neutral now, right?
Is
Hydrogen.
is positive gonna go to one of the double bonds?
It's actually going to be this carbon. And I've just generated what?
A carbocation.
A carbocation.
Is it from the H? Is the H gonna like,
That H is still there.
that H is still there? Oh, is this just positive now?
It's just, this is a positively charged carbon. Right? There was a hydrogen here as well, and it's still there. So this is a 3-bonded carbon with a carbocation.
So is that positive there because the double bond attached elsewhere?
It is. these electrons, both of these electrons are now involved in this carbon electrophile bond. So it took all those electrons from this carbon and now it's positively charged. Okay? Is that aromatic? It is not. When you look at it, it's no longer completely conjugated. It's technically not even planar anymore. It's still cyclic. Okay? It no longer satisfies Huckel's rule. So is that higher in energy or lower in energy than the starting material?
Higher.
It's higher in energy, right? It's no longer aromatic. So is this the product or an intermediate? This is an intermediate. Now this intermediate is more stable than a typical carbocation because of all the resonance structures I can draw for it. Okay, so it's more stable than a typical carbocation, but it's not as stable as the aromatic ring.
Is it also more stable because it's cyclic? Like it's in,
That certainly helps, yes. So now, but we know that we got to get back to an aromatic ring, right? So how do I do that?
The X minus will attack the hydrogen,
The hydrogen. Which the hydrogen?
the one on the same carbon as the electrophile.
Okay. So if that attacks here, it's going to be functioning as what? Is that a nucleophile or a base?
Base.
It's a base because it's attacking a proton, right? Now what happens?
The carbon hydrogen bond goes back to make a pi bond.
That's right. It's just that simple. It really is. So let's think about a reaction diagram for this. So if we plot this out, right, we've got energy here. We've got our starting material, which is our benzene, and our E+. And over here we've got our product, which maybe is a little lower in energy. Okay, and that's going to be okay, so that everything balances out. So in the first step, the energy goes up, right? And we get this intermediate carbocation. And that's a bad drawing, but it's this. Okay, trying to draw it. And then the X minus has to come in and attack the proton. Well, that's going to give you another transition state, but it's going to be low energy. And then it's going to come down and give you the product. What does that kind of look like?
the SN2.
SN2?
I mean,
One.
SN1.
SN1. It's a very similar energy diagram to the SN1 reaction, but it ain't SN1. It's electrophilic aromatic substitution. Okay? That's the general reaction mechanism. What do I mean by general reaction mechanism? I don't care what the electrophile is. They will all react like this. So what's the question that you need to be asking yourself? How do I generate the electrophile? So if I want NO2 plus to be my electrophile, so I can do nitration, you need to know I need a mixture of nitric and sulfuric acid to make that electrophile. If I want to make the bromine be the electrophile, you need to know that I need bromine plus iron tribromide. That's how I make that electrophile. If I want to make the sulfonic acid, right, the SO3H plus is the electrophile. I need SO3 and H2SO4. Okay? You need to know how to create the electrophiles because this reaction's a piece of pie. This isn't the problem. The problem is how do you generate the electrophile. Okay? So on the exam, I will most likely give you something like benzene and give you a product and ask you which of the following reagents would do that reaction. You need to know those. Do you have a question?
Yeah.
Oh, that's all right. So that's the general reaction mechanism. Okay? And it looks just like we said. right? That first transition state is when the pi bond is starting to react with the electrophile. This is the intermediate. This is that second transition state where we're starting to remove that proton, and then the final product being the substituted benzene. Okay? So it's a two-step process. It goes through a carbocation intermediate that is resonance stabilized. Okay? Halogenation, we just talked about that, right? If I take a little bit of chlorine, iron trichloride, I can make chlorobenzene. If I take bromine and iron tribromide, I can make a little bromobenzene. So what do you think would happen? And I don't have any, but if I took this solution, which is benzene plus my bromine, and I threw in a little bit of iron tribromide and shook it around, what do you think would happen?
Bromobenzene.
It would react, and what would happen?
You would get bromobenzene.
And I'd get bromobenzene, and what would happen?
Clear.
It would go colorless, right? Because we know that those halides are not colored, and in fact, that's what would happen. I'd have to sit here and shake it, but you would eventually see the color dissipate, and it would go colorless.
So why does shaking the thing make it like react faster or something?
It doesn't, well, so iron trichloride, do you think that that's going to be soluble in benzene? No, it's inorganic, right? And we know that light dissolves light. So when I put the iron tribromide in there, it will just be a solid in there. And so to get it all to mix well, you have to shake it to make sure that everything comes into contact for the reaction to occur. Okay. That's the only reason you'd have to shake it. That's really the only reason you stir reactions. Have you all had to stir some reactions in the lab so far? Right?
Or while making coffee.
While making coffee? Yeah, okay, fair enough. But in reality, if everything's mixed, you don't need to stir it. A lot of times we stir reactions just because we like to see that something's really happening. But you can actually mix things together, and if they're completely homogeneous, you actually don't have to stir them. They'll react on their own. But when things don't mix very well, you do have to stir them, so that increases the contact of the pieces. Okay. So now let's look at the general mechanism here. I know what the general mechanism is for the electrophilic aromatic substitution part. So what am I looking for here?
The Cl+.
How do I make Cl+? How do I make Br+? Do you think I can look in my catalog and order a bottle of Br+? Can't do it. It's not stable. Okay, but I can order bromine, Br. Pardon? Maybe. I'm kind of getting there. What is on the bromine that I haven't drawn in?
The electron.
Hydrogens?
No, there's no hydrogens here.
And those pairs.
It's just two bromines connected together, but there's also electron pairs, right? So there are electron pairs around the bromine as well. Are there any? Yes, ma'am.
Can you say again what this general reaction is?
This general reaction mechanism is for the generation of the electrophile. And I'm picking on bromine. Same thing for chlorine. Okay? Is there a formal charge on either of those bromines? No. Bromine, just that's what it looks like. But somehow I've got to get one of those bromines to be, or at least behave like Br+. Well, I'm going to throw in some iron tribromide. FeBr3. And it turns out that the iron in FeBr3 still wants a pair of electrons. It's electron deficient. It's a Lewis acid. Remember, Lewis acids are electron pair acceptors, right? Where do I have electron pairs? On the bromine, right? So, neutral, Br, Br. FeBr3. So if this is neutral and I give it electrons, what's going to happen to the formal charge on this iron?
Negative.
It's going to become negative. Right? If you take something that's neutral and you throw an electron into it, it becomes negative. So what happens to this neutral bromine? It gave up one of its electrons, right? It becomes positive. What do I need? What do I need my electrophile to be? Br plus. I kind of already have that, don't I?
Yeah.
But you know what? It ain't this bromine that does the reaction. What happens is bromine being positively charged, does it want to be positively charged?
No.
So it's going to pull electrons to itself. It's going to pull these electrons to itself, which makes this bromine kind of positive. And so what happens is your aromatic ring reacts with this bromine and kicks that out, okay, as a leaving group. And so what you get as your intermediate is you get your carbocation intermediate plus FeBr4 negative. This is the X minus. Okay? And so it's actually one of the bromines from this that come in and remove the hydrogen. Because it's a catalyst, I got to get FeBr3 back. Okay, and it does it by losing bromide. We're not going to talk about that mechanism. But notice, this is kind of the interesting part. It's actually the terminal bromine that does the chemistry, even though this one contains the formal positive charge. But all of this behaves like it's Br plus. And I put it in quotes. There ain't no Br plus floating around. Okay? That just by itself. Okay? That's how we end up generating the Br plus. What would we do if we threw in chlorine instead? Same thing. Same thing, it's just with chlorine, right? This turns out to be a pretty important reaction, for better or for worse. I'm going to show you a couple of examples here. Let's start with the good first. Wellbutrin, or Zyban, which is an antidepressant. Notice it has an aromatic ring with a chlorine on it. This is how you get the halogen on there. You do electrophilic aromatic substitution with chlorine and iron trichloride. You can't go to crude oil and get benzene with a chlorine on it and make Wellbutrin. You got to put it on there, okay?
There's also the ketone in that.
There is. There is too, yeah. So maybe they made it that way from Friedel-Crafts acylation. Honestly, I don't know how they make the Wellbutrin synthesis. But certainly to put the chlorine on, you're going to have to do something like what we're doing here. Chlorpheniramine. Again, we've got a chlorine on a benzene ring. This is an antihistamine. This time of year when people are having allergies, you want to get an antihistamine to relieve some of the pain and pressure. You're going to take something like that. Yep.
Can I rewind a second and
Can.
How did you know, where did you get the little, the ciclet thing right here? How did you know to put
This?
that into the BR? Yeah, like, is it just understood?
Now, well, we know we're doing electrophilic aromatic substitution on an aromatic ring, right?
Okay.
So I knew I had to have benzene. Are you asking about how do I know about the arrow?
No, I think you just really just explained it right there, because
Okay.
it's just understood.
Yeah, because we're talking about electrophilic aromatic substitution. No, because we're talking about electrophilic aromatic substitution, right? So we know that we had to put that in there. You'll also see this herbicide, this 2,4-dichlorophenoxyacetic acid, and this 2,4,5-trichlorophenoxyacetic acid. This mixture is known as Agent Orange. Okay? If you've done any studying of the Vietnam War, you know we were fighting guerrilla warfare in the jungle. Kind of hard to see the enemy with all the foliage. So what did we get the bright idea to do?
Down, down.
Well, kind of we did, I guess. But no, it was to defoliate the areas of the jungle that we were going to do battle in. So you actually had planes flying over, spreading this herbicide called Agent Orange. Okay? And it made the leaves fall off the trees, and it made the vines lose all of their leaves. And now all of a sudden I can see through the jungle. I can see better. I can see the enemy. I can do battle. I can do what I need to do. The problem with this is not only environmental, but you've probably also heard many Vietnam veterans came back with severe medical problems as a result of exposure to Agent Orange. It's true. Okay? Turns out that Agent Orange is pretty potent stuff and caused a lot of health problems. But nonetheless, those molecules were made through electrophilic aromatic substitution reactions. Okay? So you can have some good things that come out of EAS. You can also have some things that aren't so good in the long run for EAS. Okay? Nitration and sulfonation. These are actually pretty interesting reactions. So you can take benzene, nitric acid, and sulfuric acid, and you can make nitrobenzene. This is actually how you make trinitrotoluene. What is trinitrotoluene? TNT. Dynamite. That's right. What do we know about TNT?
Blows up.
It's an explosive. That's right. So what they do is they take toluene. They take nitric acid, HNO3. They take sulfuric acid. And ultimately they get trinitrotoluene. They do the reaction 3 times. NO2, NO2, NO2. Looks like a little harmless molecule. It is not. Okay? Many people have died trying to make it. The first nitro is not too bad. Second nitro, it's a little explosive. The third nitro, if you look at it wrong, it'll detonate. Okay? It's pretty nasty stuff. Okay? We no longer make it in the United States. As far as I know. Huh?
I'm sure someone, there's always that one.
Well, we have explosives that are a lot more stable than TNT these days. Things that you can actually burn and throw down, and they're a lot. I don't know that there's any explosive that's environmentally friendly, but I mean, it's relatively speaking easier to work with than TNT. We can also do the same thing with sulfonation. So let's look at the sulfonation reaction just a little bit here. The nitration reaction. The key here is to form the NO2+. Okay? So when you mix nitric acid and sulfuric acid together, you get NO2+. It looks like this. It happens very, very quickly. Okay? What's weird about that reaction mechanism?
The bottom one?
No, top one.
Make water.
You do make water. Okay, that's true. What else is weird about it? What's weird about what's going on with the nitric acid? It's donating a pair of electrons, right? So what's it functioning as? It's functioning as a Lewis base. In Gen Chem, what did you learn about nitric acid? Is it a strong acid or a weak acid?
Strong acid.
It's a strong acid. So why in the world is a strong acid functioning like a base?
Because the other acid is stronger.
That's right. Remember, acid-base chemistry. 99% of everything in the world is all relative, right? So yes, nitric acid by itself, when I dissolve it in water, completely dissociates. But when I dissolve it in sulfuric acid, it functions as a base. Okay? And so what happens is the oxygen atom that has the acidic hydrogen grabs another hydrogen from sulfuric acid and makes this oxygen with a positive charge. What did we call an oxygen with a positive charge?
Oxonium.
Oxonium ion. So we make an oxonium ion. It looks like a protonated alcohol, right? I think it's what you were trying to say, Selena. We did that in the step where we took alcohols and converted them to alkyl halides, right? So it's kind of the same first step, right? This is kind of functioning like an alcohol, reacting with a strong acid to give an oxonium ion. Does oxygen like to be positively charged?
No.
No, it's electronegative, right? So it grabs the electrons from the bond, makes water, as you rightly noted, and NO2 plus. We've just generated the electrophile. Okay? That electrophile then reacts with benzene and that general reaction mechanism that we learned.
So does that work with any acid? Like if you have a stronger acid, then the weaker acid will act as a base?
Yep, it will happen. That will happen. So if I took acetic acid and I threw it into sulfuric acid, the same kind of thing would happen. The acetic acid would pick up a proton. Okay? Sulfonation is actually a pretty easy mechanism. SO3 is a gas, you bubble it through sulfuric acid. The pi bond of the sulfur oxygen bond picks up a proton, and you end up with SO3H plus. Sulfur being positively charged, it's the electrophile. Okay? Now we have a general electrophile, we can do the chemistry that we want to do. Okay? So, let's do a couple of problems here. What am I going to get?
The chlorine is gonna add to the benzene ring,
Okay?
but ultimately the
All right, that's good. What's going to happen?
No phase when you enter.
I think I couldn't understand. I'm sorry.
NO3.
NO3 or NO2? 2. We're going to put a nitro group on. We call that nitro. It's nitration. What's going to happen?
SO2.
SO2 or? Okay.
So why did I do that? Okay, so why is the, so where is that, where does the other oxygen go?
So this is the electrophile.
Mhm.
Notice there's 3 oxygens already on that electrophile.
Mhm.
So the benzene just makes a bond between the sulfur and the benzene ring. So the SO3H is going to be attached to the benzene ring. That's what we end up with.
I meant the other one.
The other one what?
That one.
Here?
Yeah, what happened to the other oxygen?
What happened to it?
Oh, it got donated.
You tell me, what happened to it? Where'd it go?
Hey man,
Think
Well, it did go away, but where at? On the water. That's right. That third oxygen in NO3 leaves as water, right? Okay? So we're starting to see that we can do a lot of things on that benzene ring. Okay? Let's focus just a little bit on the Friedel-Crafts alkylation. Okay, so if I take a benzene ring, I react it with some alkyl halide, typically these are chlorides, I can make a new carbon-carbon bond. So if I take benzene and I use chloromethane and aluminum trichloride, what am I going to get?
all the way.
I'm going to get toluene. I just made a carbon-carbon bond. But you ought to be asking yourself a question here. What's weird about that? What did I teach you about carbocations? Rearrangement, but that's not possible here because there's only one carbon.
Methyl carbocations doesn't exist.
I told you you can't make methyl carbocations, and yet here I am telling you it's a methyl carbocation. So when did I lie to you?
It is the
I
license.
don't lie to you all the time. I actually never lied to you. You can't make a methyl carbocation and put it in a bottle, but you can make something that kind of acts like a methyl carbocation. So, let's think about this. If Colton came into the lab and he took chloromethane, we know that there's electron pairs around the chlorine, and he throws it in with aluminum trichloride. What's going to happen? Do you think aluminum trichloride is a Lewis acid or a Lewis base? Try again. Lewis acid. Why is it a Lewis acid?
It's stronger.
Well, it is strong.
Aluminum can accept more electrons.
The aluminum can accept more electrons. Why can it accept more electrons?
Transition metals.
That's not a transition metal, really.
Oh,
Iron is,
yeah,
but aluminum, right, is up here,
yeah.
and it's got 3 chlorines around it. It doesn't have an octet of electrons, right? So aluminum trichloride is going to function as a Lewis acid, and you get this, CH3, Cl, AlCl3. So what just happened to my charges? What's the aluminum now?
Negative.
Tell everybody how you know that.
Accept electrons.
Yeah, it accepted the electron, right? So it was neutral and became negative when it accepts the electron. What happened to chlorine?
Positive.
Positive. Does chlorine like to be positive?
No.
So it's going to pull electrons to itself, right?
From the carbon.
From the carbon. But it's not going to break that carbon-carbon bond or that carbon-chlorine bond completely.
Yeah.
It behaves like a carbocation, but it's not a carbocation. Yet. When I start to put other carbons around, it can be a carbocation. But for methyl, it's not really a carbocation. Right? Benzene just comes in and reacts at this, and that leaves. So it behaves like it's a carbocation.
So it's similar to the halogenation.
It's exactly like the halogenation reaction, except it ain't a halogen,
Yeah.
right? It's a carbon. Okay?
Maybe another one with the, do another example of that same one, that last one.
Of this one?
Yeah.
Let's try. Let's try ethyl or chloroethane. Okay?
So what are we reacting? Are we reacting chloroethane with benzene?
And aluminum trichloride. You got to have aluminum trichloride around. If I took chloroethane and I put it in benzene, nothing happens. It just sits there. They just stare at each other. Okay? But then when I throw in a little aluminum trichloride, that happens. Okay. And this bond isn't going to break because that would generate a real primary carbocation, which we know is unstable. It stays like that and reacts. Okay?
And it reacts with the benzene.
It reacts with the benzene. Yeah, and through this becomes the electrophile. So the benzene attacks. You end up with that intermediate that then reforms the aromatic
So
ring.
what's the product here? Is it gonna be also just a methyl group on the,
With this one,
yeah,
the product would be when you throw in the benzene, it would be ethyl benzene. Because these carbons are gonna come along with our, yep, CH3, CH2 benzene. Yep, that'll be the product. Okay? So you can see that example here, we just did that. That's the one that we did. We can also use tertiary carbons to give a carbon at the benzoic position that has no hydrogens on it. Now this one is a little different. The first step is the same. So if I take tert-butyl chloride, all right, and aluminum trichloride, walk me through it. What happens?
The same thing.
The same thing.
Yeah.
Well, tell me what that is.
The lone electron pair moves to the aluminum.
Okay?
So the chlorine becomes positively charged and
Now what happens?
the benzene acts.
The carbon chlorine bond is
It breaks,
great.
and I get a tertiary carbocation plus AlCl4 minus. Why is that okay here?
Because it's tertiary.
Because it's tertiary. I know that a tertiary carbocation can form, right? It's the same first step, but benzene can't attack this, it's too crowded. So the leaving group has to leave to give me the tertiary carbocation. Can that rearrange to a more stable carbocation?
No.
No, so it doesn't, right? But what about, Selena, if we did this? Let's see.
Would that also happen if it was secondary?
Yeah, so let's look at this. So let's say you took what would happen? Same first step, right? What happens?
It is a dope. It goes to
Okay, so this breaks, right?
Yeah.
So I get AlCl4 plus what kind of carbocation?
Second.
Secondary. Can it rearrange to a more stable? It can. I've got a hydrogen here, right?
Yeah.
That hydrogen can move, it rearranges to the tertiary carbocation. Okay? So if you start off with secondary alkyl halides, ask yourself if it can rearrange to a more stable tertiary. Okay? It will never rearrange to a primary. Okay? Friedel-Crafts acylation is kind of the same, except you start off with an acid chloride. You're still going to use aluminum trichloride. You're not going to make an alkyl benzene, you're going to make a ketone, right? So you're going to form a new carbon-carbon bond here and make a new functional group called a ketone. Acid chlorides you can buy. We call them acid chlorides because they look like carboxylic acids, except instead of an OH, they have a Cl. So if I use this acid chloride, aluminum trichloride, I'm going to get a ketone. Okay? We got just a couple more minutes. So, you all tell me how you think that's going to work. Tell me how you think that's going to work. How are we going to generate the electrophile?
Same process, except without rearrangement.
So what do I do? What happens? The CL breaks. And I get. But I told you we don't really get a carbocation, right? It really doesn't look like that. How does it look?
Fishy.
Fishy? The positive charge is actually on the oxygen.
What?
These electrons come down here to satisfy the carbocation. Remember, in your resonance rules,
Yeah.
everything here has an octet. This is why these don't rearrange. They're really not carbocations. But the nucleophile, or the aromatic ring, still attacks that carbon. Okay? Very similar to how we saw in the other examples. Okay? So we will finish up with this next time. We're almost done. So on Monday. Notice what I'm starting to do, though. I call these road maps. Notice what you can do with benzene. You can make chlorobenzene, you can make alkylbenzenes, you can make ketones, you can make sulfonic acids, you can make nitrobenzenes. You can do a lot of stuff by electrophilic aromatic substitution. Okay? Very, very important reaction. Our quiz today, I need you to turn in problem 8.28. 8.28, please.